In this video, we discuss the thermodynamics of mixing that needs to happen when you're trying to make a solution with two components. Alright, so let's try to make a solution here in which there will be a majority component that we call the solvent, and then a minority component that we call the solute. The solute in principle can be in many forms. It can be a gas, it could be a solid initially, or it could be another liquid. But it's clear that it's going to be a minority component, and that is going to be the solute. And in a prior video we have learned how to express the relative amounts of the solute and the solvent by using measures of concentration such as mole fraction, molarity, molality, and so forth. In this video we'll worry more about the thermodynamics that are involved in the mixing of the solute and the solvent. Alright, so we can predict whether that solute will dissolve in the solvent by calculating the change in Gibbs energy for the process. Right, so delta G has to be equal to delta H minus T delta S. And we can use this metric as a useful measure for the spontaneity of the process, because generally we're going to be working at constant pressure and constant temperature, and those are the conditions under which delta G can be used as a criterion for spontaneity. Right, so then let's take this delta H component to the solution process and then analyze what contributions it has. Alright, so the first one would be as follows. Well, there's actually three contributions, 1, 2, and 3, and they have various origins, right? So first, what actually has to happen is that the solute needs to be separated into individual species that then go into the solution, or while they go into the solution. So for example, if you have sodium chloride, right, the sodium ions and the chloride ions are in a crystal structure pinned to the lattice sides, but then there has to be some enthalpic contribution to separating those ions and putting them into the solution. So that would be, again, the enthalpy of separating the solute species so that they can go into the solution. If this is a liquid, for example, you're trying to dissolve maybe hydrochloric acid into water, right, you would need to separate those hydrochloric acid molecules if they're interacting with each other. The second contribution would be the penalty that you have to pay to separate the solvent molecules with each other. So let's assume that that solvent molecule is water. In water, the molecules are interacting with each other, and on average, there's about 3.4 hydrogen bonds per molecule. Right? As a molecule comes in, an ion or a gas comes in, then those hydrogen bonds between the solvent need to get separated, and that also carries an enthalpic penalty. Okay? And finally, you will have that there will be new interactions that are formed once you have the solute in the solution, right? So if this is, say, for example, a sodium ion coming from sodium chloride, then the sodium ion is going to be interacting with water molecules, okay, nearby, and that will be stabilizing because those are new interactions. Or, for example, if this is a molecule of hydrofluoric acid, then what will happen is that you might have interactions of the water molecules with the hydrofluoric acid. Okay, so those are the three contributions that you will have to the enthalpy. Again, that is the one due to separating solute species, the one due to separating solvent species, and that is the one that is produced when you have the interaction between the solute and the solvent. Obviously, these two are going to be positive. This will be endothermic processes, and then this one is going to be negative, exothermic, because you're forming new interactions. Right? So the balance of these three are going to tell you whether the enthalpy contribution to the mixing will be spontaneous or not. Positive or negative, so endothermic or exothermic. To that then, you will need to add the entropic term, which can be sometimes difficult to determine, and then with that you will be able to predict the sign of delta G and determine whether the solution process is spontaneous or not. Right, so then we're going to take a look at this enthalpy contribution for various pairs of solutes and solvents. Actually, for the solvent, we're always going to get water because that is easy enough to analyze. And then for solutes, we're going to choose a variety of different things right here. So for example, let's take an easy one, like for example O2, okay, which is a gas. So the question that you have to ask yourself is, well, how does O2 interact with water, right? So notice that here you don't have a dipole moment, you don't have anything other than dispersion forces, right? This molecule is polarizable, right? So when you have here a water molecule nearby, okay, it's quite possible that you can establish some sort of interaction, which will be the interaction of the electronic cloud of oxygen with the dipole moment that you have right here in that water molecule. As a matter of fact, something quite interesting happens in this O2 molecule, and that is that because that electronic cloud is polarizable, okay, the effect of this dipole moment on the electronic cloud will be such that it polarizes it instantaneously. All right, and now you can establish an interaction that is electrostatic in nature. All right, so that is called dipole-induced interaction, which is not very strong, okay, but it's certainly stronger than what you would have if this was, say, liquid oxygen, in which you can only have dispersion. Okay? All right, so that will be the type of interactions that you can have with O2. Now let's think about a different molecule, for example, formaldehyde as a solute. So formaldehyde is this molecule. It has a dipole moment right here, that is your negative end, that is your positive end. So when you put this in water, then you can have these sort of dipole-dipole interactions, which might be reasonably strong. Okay, something even more interesting can happen, and that is that this can act as a hydrogen bond acceptor from an OH bond in water, right? So water, you will have it right here, right? So you can have, you have here a lone pair, and that is all that you need in order to act as a hydrogen bond acceptor, especially if this already has a permanent dipole moment, and there you'll have that interaction. Notice that in this case, formaldehyde cannot be a hydrogen bond donor, okay, so you can't have that these would interact with water like this, okay, donating a hydrogen bond to this lone pair of water, and that's because you don't have a polar enough bond right there to establish a hydrogen bond. The difference in electronegativity between carbon and hydrogen is small enough that, again, there's no dipole right there, and this interaction is going to be extremely weak. The dominant interaction will be this type of interaction in which you have this bond in water establishing a hydrogen bond with that oxygen in the formaldehyde. Okay, so this is what we call dipole-dipole interaction, which has some sort of contribution from hydrogen bond. We can try to solve a different thing, for example, hydrogen fluoride. Okay, and in this case, you have that this molecule can act both as a hydrogen bond donor and as a hydrogen bond acceptor. Okay, so if it's a hydrogen bond acceptor, then it will accept a hydrogen bond from water this way. Notice that here you have fluorine, positive, positive, negative. And if it acts as a hydrogen bond donor, then you will have that interaction, right? Notice that in this case, this is a proper hydrogen bond because the dipole moment in HF is quite large, right? And that is going to give rise to a very strong interaction. Finally, what happens when you have ions here, so suppose that this is sodium plus, right? So ions are extremely well solvated in polar solvents like water because water has a negative end, okay, minus, right, which can interact with that positive ion, forming a solvation shell, which we have discussed elsewhere during the semester. Okay, that's how the solution process takes place. All right, so again, these type of interactions are the ones that you have to consider when you're trying to figure out whether the enthalpy of solution should be positive or negative, right? Notice that those are the interactions between the solute and the solvent, and those are the ones that factor into this third term, which will be the only negative term, right, exothermic term, because you're forming new interactions in the whole series. Right, to close off this video, we're going to examine with numbers the thermodynamics of mixing of sodium chloride in water. Okay, so this is going to be table salt okay, dissolving in water. All right, so here's the process. First you have sodium chloride, and we can try to divide this into useful steps that are supposed to augment our understanding of the various steps that are required in the solution process. Right? Notice that overall, your reaction would be something like this, or your solution process would be something like this. Sodium chloride, which is a solid, okay, ends up as sodium plus aqueous plus chloride aqueous. Right? And we're trying to see what is the delta H, delta G, delta H, and delta S for this process. Well, we can already figure out what the sign of delta G is, because we know that this process happens, right? When you sprinkle a little bit of table salt on water, that salt dissolves, right, at constant pressure and temperature. So that means that this is a negative number. Okay. The question then is, what are the numbers that we have for delta H and delta S? Right, so for delta H, we're going to try to figure out all three contributions that we have play. Okay, the first thing that you would need to do is separate those ions from the solid into the gas phase. Okay, and clearly this is going to be a highly endothermic process. And that is because here you have the ions interacting in the solid very strongly through Coulomb interactions, electrostatic interactions. And here you have the ions completely separated in the gas phase, not interacting, right? So here you actually have to pay quite a bit of energy. This number actually happens to be 786 kilojoules per mole, positive. It's endothermic, okay? And then there will be another process, which is, well, water separating to accept this hydrogen atom, these ions, and then you will have the interaction of the ions with that water, or those water molecules. But of course, separating water molecules is very difficult. Instead, we're going to consider the second and the third steps together and try to measure what that energy is. Right? So you will have something like this: sodium plus in the gas phase plus chloride minus in the gas phase plus water liquid to generate sodium plus aqueous plus chloride minus aqueous plus the disordered water, which you need, H2O liquid. Alright, so here in this case we have that there will be some penalty from the separation of water molecules to accommodate those ions, but then there's going to be very strong interactions between the water molecules and the ions, as you have here exemplified by sodium plus. You will have the same thing for chloride minus, but in this case the positive end of water will be interacting with that negative ion. Anyways, those two steps actually have an enthalpy of minus 783 kilojoules per mole. Okay, so the overall enthalpy for the solution of sodium chloride that is solid into sodium plus and chloride minus as ions in water actually has a delta H overall, which is plus 3 kilojoules per mole. This solution process is slightly endothermic. So what you can actually expect to find is that when you dissolve a little bit of sodium chloride in water, okay, the temperature of the water should go down by just a little bit, because there's some energy that is needed to give rise to that process. And that energy can be obtained from the thermal environment in which the water is, which then should get a little cooler. Okay, so then we have that this delta H is actually positive. Okay, what that necessarily means is that this term right here has to be negative, and what that means is that the change in entropy has to be positive. Okay, so then we can try to see in these steps whether the entropy changes or not. Clearly, there's going to be a huge gain in entropy in this first step, because you're going from a situation which is highly ordered, right? That sodium and chloride ions beautifully pinned down in the crystallographic structure, to a situation in which those ions are not ordered at all. They are in the gas phase completely independent, right? So the delta S for this is actually very, very, very large. Now you lose some of that entropy when you put this in solution, okay, but overall what has to happen is that when you add the entropy of all of the steps, right, that has to be positive, because we know that the enthalpy is positive, but the process takes place either way. Okay, so a conclusion from this study is that the dissolution of sodium chloride in water is actually an entropically driven process. Enthalpy alone would not be enough to make the process happen. It's just the gain in entropy that actually leads to the spontaneity of this process. Right, so let me wrap up this video. Here we have seen a superficial analysis of the thermodynamics involved in mixing. We have examined both the enthalpic contribution to mixing and the entropic contribution to mixing to determine whether various solvation processes will be spontaneous or not.